Offense is the best defense. This is 1027 longest arithmetic subsequence. Okay, so you're given an array nums of integers. Return the length of the longest arithmetic subsequence in nums. Okay, so first, what's a subsequence? A subsequence is essentially just taking an array and choosing in order elements from that array. Another way of stating that is saying that you take an array and then you delete some or no elements without changing the order of the remaining elements, right? So if you have 9, 4, 7, 2, 10, 4, 7, 10 is a subsequence, right? Because I can choose 4, then I can choose 7, then I can choose 10. Or saying that in a different way, I can take this first array, I can eliminate 9, and I can eliminate 2. You get a subsequence, hopefully, if you're doing this problem. If you're approaching a medium problem, you know what a subsequence is. And then this arithmetic subsequence. So a sequence is arithmetic if the sequence at index I plus 1 minus sequence I plus 1 minus sequence of I are the same for all values. So that basically means that the difference between any two consecutive elements is the same, right? So this whole system here is an arithmetic subsequence, right? So I can pick the whole thing as a subsequence, right? Because I can choose any element in the array to make the subsequence in order. So that means I can choose all of them. So choosing all the elements is a valid subsequence. And then it's an arithmetic subsequence, right? Because the difference between any two elements is the same, right? The difference between 6 and 3 is 3, okay? The difference between 9 and 6 is 3, okay? The difference between 12 and 9 is 3, right? So basically that's just saying if you take any two consecutive elements, the difference between them is the same. Okay, so how do we solve this problem? This one makes sense, right? The output's 4 because, you choose all the elements and then you get something of length 4 and it meets, both of the constraints of the problem statement. So maybe this wouldn't be the best example to utilize if you're trying to derive some sort of solution through the, working an example. I think this one's pretty good, right? Because we got an actual subsequence that we choose. So how do we know that we would choose this one to be the best one? And then this one's even better, right? We got the longest subsequence, 20, 15, 10, 5. So 20, it goes to 15, and then 15 to 10, and 10 to 5, right? There's a difference of -5 to each of these consecutive elements. All right, so where should we begin? Well, I guess one thing you should note in this problem, and this is a luxury of doing a Leetcode problem versus being in an actual interview, is that we have a pretty small, pretty tight boundary on the length of nums, right? Nums length is less than 1,000. So, that's a pretty small input size for the array that we're given, right? Nums, because all we're given in the system is nums. So it's, less than or equal to 10 to the 3. So an n squared solution would be sufficient, right? Right, because 10 to the 3 times 10 to the 3 is 10 to the 6. So these constraints indicate or imply, rather, that this problem probably has an n squared solution that will pass. Now, that's good because there seems to be a pretty intuitive brute force approach, which, just thinking through it right now, would be probably n squared. But in an interview, you may not be given this information, so I don't know how I would approach that. But looking at this, knowing that n squared, I kind of know, okay, I could shoot for n squared, and that'll be good enough. So what would be the n squared solution? Well, what we're really trying to do is find the maximum number of, connections between nodes. So if that doesn't make sense, let's just go ahead and graph this system. So we're not going to use this as a working example because it's a little too simple, right? We just choose everything. So we're not going to see any contrast between when you choose something and when you don't choose something because you're choosing everything. So let's just use this example, and that's also an important point. I think I already stated, I stated that, a minute ago, but the idea is use an example which is likely to give you some information that the other might not be able to provide, right? Using this example won't provide you with anything really useful, and you'll probably just waste a couple minutes, learning nothing from that working example. Okay. So let's go ahead and draw out this example. So we have nodes 9, we got node 4, node 7, node element, whatever. Maybe my terminology isn't great. So how do we know to attach something or not attach something? What does that look like? Well, I guess one observation you can make is that, you can attach yourself to any other node, right? An element can form a sequence of length 2 with any other element, okay? So that means if I wanted to know the longest arithmetic subsequence ending in 9, well, right, I can't choose anything before 9, so it would just be 9 itself of length 1. But what about 4? Well, I can attach 9 to 4, right? That's a valid arithmetic subsequence, and it has, I'm going to call this the difference, okay? So the difference is the value of the edge that connects these two nodes, right? In this system, there's a difference of 3 from 4 to 7, and a difference from 3 from 7 to 10, right? But I can attach myself to 9, and I'll say, okay, 4 can attach to 9 if there's a difference between them used of -5, okay? Then that's the same argument I can make for 7 and 4 and 9 and 7, right? 4 can attach to 7 using a difference of 3, and 9 can also attach to 7. Use a different color. We're going to run out of colors, but it's fine for now. With a difference of -2. Right, so the longest subsequence ending at 7, the longest arithmetic subsequence ending at 7 has length 2, right? And it's either 7 and 4 or 9 and 7, right? And then same for 2, right? So 2 can attach to everything before it, right? So from 2, you can go directly from 7, and that'll have a length -5. You can go directly from 4, and that would have length difference -2. And they can go from 9, we're running out of colors here. I'll just use black, whatever. You can go from 9 to 2 with length -7, right? Notice we haven't found any multi-length chain, right? Because in order for this thing to be a sequence, right? In order for this system to be an arithmetic subsequence, we would need there to be the same difference between consecutive nodes, right? So 2 may attach to 4 and 4 may attach to 9, but since 2 attaches to 4 with -2 and 4 attaches to 9 with -5, we can't create an additional subsequence, if that makes sense, right? I can't go from -5 to -2 because that breaks this idea of being arithmetic, all right? Finally, when we look at 10 and we look at everything 10 can connect to, well, what can we say here? Well, from 2 to 10, right, we get, let's use a different color. It's a +8 path, so in order for 2 and 10 to connect, they have to use a difference of 8, an edge between them. What about 7 and 10? Well, 7 and 10, we get kind of what we've been looking for, right? So from 7 to 10, in order for them to connect, they're going to have to use a difference of 3, so their edge connecting them has to be 3, but also 7 has a node going into it that has a difference of 3, right? And we could just continue doing this for the rest of the system, whatever. Let's just do it for the sake of doing it. So this would be 6, and then finally there would be a path of 1 going here, right? So there's this right, there's this whole system here, and you'll notice, well, if I wanted to look at the longest path where, each edge was the same, well, there's this path here with 4 of 3 and 3 here. Now, the actual path doesn't really matter. We just need the length of the path because that's what we're returning here. So this really gives us too much information, right? From this, we know, okay, there is a path of length 3. The longest arithmetic sequence is 4 to 7 and 7 to 10. And how do I know that? Well, because from 4, I can use the 3 path to get to 7, and then I can use that same 3 path to get to 10. All right? But another way of thinking about this without having to draw all these links and consider these nodes is just for each node, keep track of the longest arithmetic sequence using a value up to a node. So what I'm basically saying is like up to 7, right? There's an arithmetic sequence of length 2 using -2. There's an arithmetic sequence of length 2 using 3. There's a arithmetic sequence of length 1 for anything else. And what I mean by that is like for any node, right, it can attach a length 1 sequence to any subsequent node, right? Like 9, for any difference, it can connect, right? So what I'm basically saying is like, I can connect 4 to 9 with difference -5, and that makes a length 2 path, right? I can connect 7 to 9 using -2, and that creates a length 2 path. So what you can think of is like, there's a length 1 path for any value difference, right? Because for any value difference, I can connect myself with a difference to that previous node. If that doesn't make sense, maybe a working example will, maybe if I walk through this working example with that idea, it will help a little bit. Okay, so we have 9, 4. So I'm going to do the same problem again, but I'm not going to keep track of the actual paths, just what values I can use for differences and what the subsequence length is I can get using that value as that arithmetic step, right? Because there's this arithmetic step here, right? The arithmetic step here is 3. I arithmetic step 3, and I arithmetic step 3 again, right? So for each node, I'll just keep track of, okay, if you want to use arithmetic step size of 3, here's the path that I can provide, okay? So when I have 9, 4, 7, 2, and 10, 9 basically says, okay, I'm shit out of luck. I can't, oh, fudge, I just cursed. I can't connect anybody to my left, so I'm just here all alone. All right, but 4 can say, okay, 4 says to 9, hey, I want to connect to you. And 9 says, all right, well, in order to connect to me, you're going to have to use an edge length of -5, right? Let's use a different color. So I'm going to split these nodes up just so I can kind of make it clear what's going on here. So 4 can say, okay, well, I can use -5 to connect to 9. And then I'll ask 9, hey, 9, do you have any arithmetic sequences connecting to you that use an edge length of -5? And 9 says, no, I don't. I don't have anything to provide you. But I can provide myself, so you can attach yourself to me and add 1. So 9 can essentially provide -5 with length 1. And then 4 can attach itself to that and give you length 2. Now 7 goes back. 7 goes to 4 and says, okay, I want to attach to 4, so I'm going to have to use a slice size of 3. And then I ask for, okay, a slice size. I have to use a different size of 3. Then I ask for, hey, 4, do you have any arithmetic sequences going into you that use this difference of 3? And it's going to say, no, I don't, but I can provide myself, right? And then it says, okay, I'll just connect to you. And then it asks 9, and 9 says, okay, well, in order for us to connect, we have to use a difference of -2. I have nothing to provide you, but you can connect yourself to me because I can provide you with a difference of -2 of size 1. And then you can connect yourself to that, so then -2 size 2. Okay, then we do 2, same thing. I ask this for -5. It has nothing to give me, so I get -5 size 2. It means this can provide -5 size 1. I ask this thing, it says -2 is the best I can give you, -2 size 1, so I can do -2 size 2 here, connecting 2 to 4. And then I ask 9, okay, this thing says, oh, I can provide you with -7 size 1, so this becomes -7 size 2. Okay, now finally this one, okay? So 10 wants to connect to 2, right? And it says, okay, do you have 8 to provide me? No, I don't, but I can give you myself alone, so that means 8 size 2. I ask 7, hey, 7, in order to connect, we're going to need 3. All right, now here's kind of where the golden point is. And 7, and I say, 7, what's the longest path you have using a difference of 3, an arithmetic sequence using a difference of 3 connecting to you? And 7 says, well, actually, it looks like I have, using a step size of 3, right, using a difference of 3, well, there's actually a path of length 2 connecting to me. And 10 says, okay, cool. So you have a path using difference 3 that's size 2, so I can connect myself to you and you connect yourself to it, and together we can get a path of size 3. All right, which is the same thing here, right? When 10 connects to 7, 10 goes to 7 and says, okay, we're going to have to use a path size of 3, and 7 says, oh, well, it actually turns out that I also can use a path size of difference of 3, and I'll connect to that, and then I'll connect to you so I can provide you with that information. So it's a very dynamic programming-esque kind of idea, right? So I have to use 3 to connect to 7, and 7 says, okay, if you want to use a different size of 3, well, I can provide you with a path of length 2. And 10 says, okay, then I'll attach myself to that path and make this size 3. Okay, and then it would do the same thing for 4, right? So 4 would say, I need 6. It says, I don't have 6. So then it's 6 of 2. Then I connect myself to 9. 9 says, okay, I don't have a difference of 1. but I can provide you with just myself for a difference of one path, length of two. And at the end, you would just look at all these values, right? And you'd say, okay, which one is the maximum? And that would result in my maximum path, and that just turns out to be this path here. So generally speaking, right, if you have an ith node, I guess the dynamic programming relationship here, so the ith node, if the ith node wants to connect to the jth node, what would that mean? Right, so the dp of the ith node connecting to the jth node would be the value of the ith node minus the value of the jth node. Basically what I'm saying here, right, is in order for 10, let's say 10 is the ith node and 7 is the jth node. For 10 to connect to 7, they're going to have to use a value difference of 3. So that's what I'm saying here, right? So if I want to connect to that previous node, we have to use the difference of our value. So if at this node, the path that I can get going to this node using this value, connecting to the jth node, right? Because in order to connect to the jth node, I would have to use the value of me minus the value of the jth node, right? It's going to be, well, it's going to be what? It's going to be 1, because I'm going to attach myself, right? Plus whatever the largest path is that jth node can provide me using that same value. Okay, I'm going to have to move this over. I apologize. But I think this makes sense. Right? So the value ending at my node, the arithmetic subsequence ending at my node, using the value I'd have to use to connect to the jth node, is 1 plus whatever the value is, whatever the longest arithmetic sequence is at the jth node using that same value. Right? So if we had, just in our example, we had our ith node here, or no. We have our jth node here and our ith node here. Remember, it was, It was 10 and 7. Right, so we had the value of this node was 10 minus 7, and then 1 plus 10 minus 7. Right, so this is 3 and 3, and then we saw in this problem before, right, we have to use the 3 value, so the 3 value for 7 is 2. So I get this value, which would become 2. So then in order for the ith node to connect to the jth node, I'd get a path of size 1 plus 2, which equals 3. So hopefully that makes a little bit of sense here, right? The basic idea is if I want to connect to the jth node from the ith node, right, I'd have to use the value that results when I subtract my value minus the node I'm trying to connect to, because that would be the arithmetic difference I'd have to use. So then the maximum subsequence I would get would be 1 plus, because I'm connecting myself to it, so I get 1 extra node plus whatever the longest path it can provide using that same step size, and then you'll get the longest step size using that idea. Okay, so with that, let's go ahead and try to solve this. So each path, right, we noticed when we were solving this problem, right, like, everything was always able to provide at least a path of size 1, right? You can always provide a path of size 1 because you just send yourself for any difference value. So in order to kind of do that, so we'll create a dp equals default dict, and then you can always provide a path of size 1, okay? And then we'll look at each index in range length of nums. And then we'll look at everything that comes before you, right? Because for every ith node, you look at, we'll call it ith and jth because I use that language, right? For every ith node, we looked at everything that came before it to make a decision about what it could connect to and what that would look like. So for jth in range, we'll only have to go up to the ith node. The ith node itself. No, just the ith node. Okay, so dp of what? Of the ith node using this value. So maybe we can just do a comma pair to correspond to this idea here. Right, so the dynamic programming catch for this ith node using the value in between them, okay? So we have the ith node, and then what's the value between them? That would be nums at the ith node minus nums at the jth node equals... We're only looking at the node once. Okay. The max, not the maximum. The D1 plus, so I can attach myself to whatever path I can provide me with at the jth node for that same value. Sorry about the way I look today. I'm just all over the place today. Okay. Nums of the jth value. And then at the end, we would just return the max of the values that we can get. Oh, I always forget this is a function. I don't know why I do that. It's obviously a function. Obviously speaking, it's a function. Okay. Ain't nobody praying for me. All right, cool. So it's very slow, probably because I'm using a default dict. But I'm not gonna worry myself too much with this because I'm pretty confident that n squared is the... I mean, it's sufficient, obviously. All right, but. Okay, it's probably because I'm using a default dict. We're using, yeah, look at that. So, again, that's an important point, is don't concern yourself so much with the fact that, you know, something may or may not be super fast when you run it, because in the you know, Leetcode solution, because the runtime can vary greatly depending on, you know, small factors. But let's go ahead and look at the runtime. So if n equals the length of nums, okay. For time, well, we have to look at each number, and then for each number, we have to look at all the numbers that come before it. So for n numbers, we have to look at the, you know, the proportional to n numbers that come before it. So that's going to be big O of n squared. Okay, and then space. Well, for each, we keep information about each node that comes before us, right? Because for each node that comes before us, we get a certain chain that we get to add in, right? So for, you notice we're updating the DP for the ith node minus the jth node at the ith node for each node, right? And for each node, you have to do that for all the nodes that come before it. So that's also big O of n squared. So this is a big O of n squared time, n squared space. All right. Peace out, guys.